Good morning, class, and welcome to this lesson on fluids for Pascal's principle. Today we will be able to define Pascal's principle and be able to apply the equation for a conceptual situation. So we're not going to do any math today. We're just going to look at what Pascal's principle is and then kind of look at what that means in real life. So Pascal's principle, let's define it. Pascal's principle states any change in the pressure applied to a completely enclosed fluid, okay, that's a key point right there, completely enclosed fluid, is transmitted undiminished to all parts of the fluid and enclosing walls. Okay, walls. Sorry about that. So any change in the pressure applied to a completely enclosed fluid is transmitted undiminished to all parts of the fluid and enclosing walls. We end up getting an equation for this. Basically, that P2 equals P1. And where I get this from is I go back to P2 equals P1 plus rho GH. But we're going to look at a situation here where these two levels are the same. So this level is the same as this level. And so what's going to happen is we're going to apply pressure here, and then in turn this is going to apply pressure up. And because these two are at the same level, rho GH, well, the change in height is 0 because these are at the same level. So P2 equals P1. So that means that F2 over A2 equals F1 over A1, because pressure is force over area. So if I apply a force over this area, what force is going to be applied on this area? And so if we just bring this over, if we multiply both sides by A2, we can now calculate what the force is going to be on the opposite side. So let's look at this picture over here. This is how car lifts work. This is how we lift up a car. Because let's just say the area of this tube right here, let's just call this 1 meter squared. Okay? And let's say the area of this thing is 5 meters squared. Well, so if I apply a force of 1 newton, or a force of 1 newton on this side, 1 newton over 1 meter squared, that's a pressure of 1 Pascal. This pressure is going to travel undiminished through this tube, and because there's a larger area, I am now going to get 5 newtons of lift on this side. So because I applied a small force to a small area, it travels undiminished, and because every single 1 meter squared is still going to provide a force of 1 newton, because that's the pressure, it's going to now move with a force of 5 newtons. So by applying a force of 1 newton, I get a force of 5 newtons on the other side, because that's the ratio. Because if we did F1 over A1 equals F2 over A2, F1 would be 1 newton, A1 is 1 meter squared, A2 is 5 meters squared, and so we're going to get a force of 5 newtons on the other side. So this is how we are able to lift up cars and other heavy objects with a very small input force, because if you put a small force in, you're going to get a large force out. And you might say, but how does that work? That seems kind of like conservation of energy is not being obeyed. It seems kind of untrue with other things we've learned. The catch is, if I push this thing down 5 meters, this is only going to move up 1 meter. So the amount of work done, the amount of energy, it balances out, because work equals force times distance. So if my force is 5 times bigger, that means my distance is going to be 5 times smaller. So we have to have a large distance here to make up for this small distance here. But for lifting most objects, like a car, we don't need to lift it up very high. So this is how it works. Pascal's principle means that force or pressure, is transmitted undiminished. So for every 1 meter squared here, it's going to have the same output over here. For every 1 Newton and 1 meter squared on this side, I'm going to get 1 Newton per 1 meter squared on this side. So this is kind of how if you've ever been to like the salon or the barber, okay, whatever your preference is, and you're sitting in your barber's chair, okay, you're sitting in your barber's chair. And they have a little hydraulic press here, and they have this little lever, right? And they step on the lever here, and you raise up. And it doesn't really seem to matter how heavy you are. You have heavy guys in the chairs, you have skinny guys, skinny girls, big girls, whatever. This person doesn't seem to really work very hard to lift you up. Well, if you weigh 150, 200 pounds, that's a heavy weight. The reality is there's a mechanism in here that's very similar to this, where the person pushing down on the lever is pushing on a very small area, and the output is pushing up on you to lift you up. So that's how how a barber's chair works, to lift you up. And you notice that when they lift you up, they're cranking on this. They crank on it like 10 times to lift you up like half a foot, because energy is conserved. If they put a small force in over a larger area, that means the amount of distance it's going to travel is going to be even less. So they really have to crank on it a lot of times to get you to the height that you need to be. So here's another example. This is how some places dump out their trucks. They literally just pull the truck onto a bed, and this entire thing lifts up. And this is a demonstration of Pascal's principle. Same thing here. This is the output force, and there's an input piston over here somewhere, and they're probably going opposite on this one. So F1 over A1 equals F2 over A2. They're probably working over a smaller area on this one, and because it's a smaller area, you're going to get more distance. So because it's a smaller area, just like if we go back to the last example, let me just clarify again. We had a smaller area pushed to a larger area, but the distance it traveled was less. Okay? Well, in the opposite situation, we're going to go to a smaller area, so the distance traveled is going to be more. That's how they get this entire truck up really, really high. I mean, this is a big old truck, but it's just the same thing. They're using fluids, hydraulics, in order to lift this up. And they're just using Pascal's principle and these different ratios to figure that out. And because in this situation, this has to travel a very large distance. So as you can see, this is Pascal's principle. Pressure travels undiminished to all parts throughout a fluid, including the outside walls.